Okay, so we're at 4 o'clock, so we can go ahead and get started. So it's my great pleasure to introduce Zdenek Strakos, who is a professor at the Faculty of Mathematics and Physics at Charles University. Among his many other accomplishments, he's a SIAM Fellow, he's the winner of a SIAG LA Best Paper Prize, and he is very well known for his work on Krylov subspace methods, and in particular, their deep connections with other areas of mathematics. And in addition to being a great mathematician, I consider Zdenek to be a great friend and colleague. So I'm very happy to be able to introduce him here today. So Zdenek, please go ahead.
Thank you very much, Erin. I do appreciate your nice introduction. And first of all, I would like to give my thanks to organizers for giving me this opportunity to speak again. And I am really sorry for the trouble that was caused by these technical issues the last week, and I do appreciate very much your kindness and also nice words that of encouragement that I've got from couple of you. So I hope that you will consider this time that nothing will happen this time, and they will consider this 1 hour worth. As Erin said, I'm going to present results that connect infinite dimensional view to the problem and finite dimensional view to algebraic computations. And this is a joint work together with my colleagues. My last student, Tomas Gergelits, graduated about 1.5 years ago, and 2 colleagues from Norway, Kent-Andre Mardal and Bjørn Fredrik Nielsen, who I'm indebted not only for working on, but also for introducing me to this problem. Okay. So, in the infinite dimensional setting, the problem is just stated in a Hilbert space for us. And of course, if we wish to compute, we have to say restrict it to the subspace, which is finite dimensional. And after using basis, we'll get algebraic combination, algebraic formulation. That's obvious in terms of matrices and vectors. And but it's useful to look, if we wish to solve the problem, if the problem is large, we wish to solve it by Krylov subspace methods. Here we will use conjugate gradients because the problems will be self-adjoint and also coercive. So then it's good to think about what is the main principle. And main principle of Krylov subspace methods is essentially the approximation of the inverse of the operator with respect to a given vector. And which approximation we have in hand? Well, we cannot use the inverse, so the polynomial approximation is only what we can do, and that leads us to Krylov subspaces. So it's a very natural thing, so that's what the Krylov subspace methods are. And what is interesting to see that almost immediately after, say, establishing the main methods like Lanczos method and conjugate gradient methods in algebra, they were established also in infinite dimensional Hilbert spaces by Karush, Hayes, Steffs, Vorobiev, etc. And even these early papers, it's very significant results like superlinear convergence in infinite dimensional setting were proved. So these papers are really, really beautiful. Well, if we take this residual, if we take this polynomial and go from the solution to the residual, so we immediately get what we are used to when we open the algebraic textbook. So we, for a given method M, we see that the residual is defined by the polynomial in the operator applied to the initial residual. And this polynomial, of course, has a value 1 at 0 by construction. There is a lot of mathematics, very deep mathematics, and in many areas that is related to Krylov subspace methods, and that they were existing much before the Krylov subspace methods were born. I'm not going through them, but we will touch some of those. In particular, we'll touch the spectral representation of operators later. But who would like to see more on that, then I recommend our book with, well, of course I'm biased, but one can look at our book with Gergelits, where we have a lot of historical remarks on these issues. Okay, so what will be an important issue for us is this motivating example. We took it from standard, say, very nice and well-known paper but is used also in the other paper, is a classical model problem. But this model problem is related to applications. It really represents the class of issues class of problems that need to be resolved in practice. So we have essentially divergence of k times the gradient. That's the operator, and k is a function. And here it's just one-dimensional function. And the problem is discretized using about 4,000 degrees of freedom. And the k in this model problem is we have a domain. Domain is divided into 4 subdomains. A k is constant in 2 subdomains, and with the different value of the constant in the other 2 subdomains. And then we may look at this problem and use discretize, just using standard finite elements, Laplace discretization, Lagrange elements, the linear element, that's standard, easy, that's why it's also used in the paper. And then apply incomplete Cholesky preconditioning or Laplace operator preconditioning, which essentially uses this operator with k is equal to 1. And that would happen. So we look at the convergence curve. So we'll see that if we use the incomplete Cholesky, we'll get a blue convergence. If we use Laplace preconditioning, we'll get a red convergence. But there is a puzzle, because for the Laplace operator preconditioning, the condition number is equal to about 160, while for the blue is about 1 order of magnitude less. But the red curve is, of course, much better. Convergence is much faster than the blue. So what's going on? So that's what we are going to address in this talk. So first, let's recall a few words about spectral information and convergence of conjugate gradient method. That's material that has been lectured many times, but I'll go through that quickly. And then we have 4 papers actually. I will just recall basic, most important results from all these papers. It will give us a story and then few comments on the spectrum and eigenvalues relationship. Okay, so here's the motivating example again. So we would like to know what are, for example, in particular this slope here, where the convergence is almost linear, for Laplace very fast, for incomplete Cholesky less fast. And this starts after the first 5th iteration. So why after the first 5 iterations? Okay, what's going on this first 5 iterations and later on? We would like to explain that. Okay, so if mentioned that we use spectral representation, so for matrices, it's easy. We'll just do transformation to the orthonormal basis of the eigenvectors. But for infinite dimensional, it's a little bit more complicated. We'll use just a sequence of projectors. But this is what I've mentioned on this historical slide where I mentioned the spectral representations, which due to von Neumann and Hilbert and the others. So we can write the representational operator using the Riemann-Stieltjes integral, and we can define the distribution function using this family of projectors with respect to the given starting normalized residual. And spectrum of the operator is, of course, defined not as the eigenvalues, because it can have a continuous part. This operator is self-adjoint, so we don't have anything else than the continuous part and discrete part. And of course, it's just a complement of the residual set. For the matrices, things are simpler. I've already said we have the distribution function is just the stepwise functions defined by the individual eigenvalues, and the sizes of the steps that are determined by the projections of the normalized initial residual in the direction of the individual invariant subspaces. Okay, now what are the questions? So the first question is, so we have said that the behavior of conjugate gradient method for this self-adjoint case is determined by the distribution function. So we should describe a little bit more. That will be easy because it is now, I would say, textbook or monograph describe the material. But the more important thing, new thing, more original thing is we should ask what is the relationship between this distribution function of the problem in this infinite dimension and this stepwise function that we'll get for matrices when we discretize. And then we refine discretization, for example. So what will happen? And what will happen in the process of CG then also? Okay? And there'll be a problem, and this problem I would call it as a wall of the compact to non-compact operators, between the compact and non-compact operators. And lastly, is there any way how to get for a given class of problems, or a generalized class of problems than the model problem, anything about the spectra of the matrices arising from discretization a priori, without doing any computations? So without computing the angles, computing the spectra of the matrices. There are the questions that are in front of us. So the first one is easy, as I've said, because we all know that for CG essentially can be viewed as a Gauss-Christoffel quadrature. If we just take the original distribution function, omega, defined, say, on the infinite dimensional problem, and integrate the function lambda to the -1, because we are essentially approximating inversion of the operator. So it very well makes sense. What we'll get is just at the end step and the Gauss quadrature, because the original integral can be written just as a normalized square error. And then this represents just nothing but the Gauss quadrature. And here, what we'll get is the error of the CG, and that's the same thing as the error of the Gauss quadrature itself. Okay, so CG and the Gauss quadrature are essentially the same, only using different language. I see that Rachel Hook is raising hand, so I don't know if she should do it now or later on. Later on, perhaps.
Zdenek, good morning for me, good afternoon for you. Could you back up a slide, please?
Okay.
Yeah, so naively, my understanding that one way to answer your first question here is that the precondition must be spectrally equivalent to the operator. Are you going to point out that that's not enough, that you can do more than that?
That's exactly what I'm saying, because spectral equivalence will give you only independence on discretization or on some parameters, but will not give you fast convergence. Okay.
Okay, thank you.
Okay, so we have this spectral representation, as I mentioned, and the spectral representation for the matrix will give us this distribution function, okay, which is just a stepwise function for the finite dimension. And here we have these three questions. And as I've said, the key concept here is using this Gauss quadrature, because that's what we do. CG does the Gauss quadrature essentially for this distribution function and generates the sequence of Gauss quadrature approximations to these distribution functions. And that's what governs the convergence of CG. Okay, so that's what I've just written here. So that's why these other two questions that I mentioned are the key questions. So we should understand first, what is this distribution function omega? And the second, how it is approximated in the process of computations. Well, this all can be done. This the last issue can be done and is described well in our book with Gergelits, for example. But one can ask a question, well, this is all fine in exact arithmetic because it's based on orthogonal polynomials and in principle on orthogonality and on the fact that CG is nothing but the Galerkin method with using a special Krylov subspace for, say, kind of discretization or mimicking discretization. What about running errors? But fortunately, we have this very nice theory, mainly due to Chris Page and Greenbaum and many others, which says that in finite precision arithmetic, essentially we can work exactly with the same model. We can again work with the distribution functions, only we have to replace individual eigenvalues by tight clusters. And we can use essentially the same mathematical theory. So rounding errors will not cause a problem to our reasoning. So again, that's what we are going to describe. Okay, so this is the common wisdom that everything things are governed by the condition number, but here definitely something is wrong because the condition number is larger and the convergence is much faster. So why it is so? Now we will talk about, say, experimental evidence. So after we compute, so we see what now I'm going to present, and then I will return back to what we can say a priori, and will come that we can have the same view or the same explanation without this computation. So what we see, this very fast convergence in Laplace preconditioning is related to the fact that after the 5th iteration, only this very small, tiny part of the distribution function is actually affecting the convergence. The rest is for the process non-existent. The process doesn't see it anymore, starting from the 5th iteration. While from the Cholesky preconditioner, this is not true. For the Cholesky preconditioner, still a very large part of this distribution function governs the iteration. So essentially only a little part at the lower end is eliminated, but nothing else happens. So that's why the convergence is almost linear from the very beginning to the very end. Of course, here the horizontal scales are different because this is one order of magnitude shorter than that, okay? But this is very tiny. That's why the convergence is much faster. So to elaborate on that, so what we can find if we compute, so this is the 5th iteration. At the 5th iteration, we have 5 Ritz values, 1, 2, 3, 4, 5. This is for the Laplace precondition. And what are the eigenvalues of this precondition matrix? We see that we have the smallest eigenvalue, which is this eigenvalue is equal to 1, has multiplicity almost 2000. Okay, we have the largest eigenvalue, which has a multiplicity again almost 2000, and its value is 161.45, and something in between. And something in between here, these angles here in between have such a small cumulative weight that simply processes don't see it. And on the other part, these angles are approximated in this first 5 iterations. So essentially, this angle, this angle, this angle, this angle is eliminated in these first five iterations, and the same that one angle. Okay. Angles on the left, we'll talk about that a little bit later. This elimination holds for forever because it is not affected by rounding errors. If we'll continue the iterations, then we will see that new Ritz values will appear here, but they don't manage because the convergence is so fast that simply it doesn't, this phenomenon doesn't happen. So rounding errors, they don't affect this computation very much. And that's why the convergence starting from the 6th iteration is just governed by very tiny part of the spectrum between those two eigenvalues. That's what was seen on the other picture. How it is with the Cholesky, that's different because here on the upper part of the spectrum, there's nothing to approximate essentially. So we stay with this. Only very few eigenvalues on the left are eliminated. So we still stay with these two red eigenvalues. And that's why the convergence is so slow, because it's almost linear, because the process sees this whole thing as essentially compact interval full of eigenvalues. There's nothing to adapt to. This point on the lower end of the spectrum and no problem with the rounding errors can be attributed or can be explained very nicely by beautiful theorem by van der Stoel and van der Forst in their paper from '86, and then interpretation that rounding errors simply do not play a role, and little strengthening of this can be found in our book with Gergelits and this one. Okay, so this is all about convergence. That's what we need. So what I was talking about up to now was just experimental observation. Okay, if we compute, that's what we observe. So we explain experimentally why the convergence was how it was. And now we do the same, just without computation. So everything started with this seminal paper by Nielsen, Twaito, and Hagbush from 2009. And also, everything started for me because I didn't know that paper until this 2018 ENUMAD meeting in Bergen, where Kent André Mardal have approached me and said, well, you know, I've made some experiments related to that paper, and there is an issue that we are unable to explain. And he gave me the paper and explained the question. And said that's how our work started. So I will first explain what is the main result in that paper. So this paper is about infinite dimensional spectra. Okay, so let's take this operator from the model problem, and K is just a scalar right-valued function, and it's uniformly positive. So we consider the operator self-adjoint and coercive. So the theorem says then for all points in omega at which Kx is continuous, the value of Kx must be a part of the spectrum of the preconditioned operator with the Laplace precondition. So that means that, for example, if we have K a continuous function throughout the closure of the domain, that means that the closure of image of the whole domain must belong to the spectrum. Okay, very interesting result. And of course, A and B are the operators defined as typically they are in Sokolov spaces. Okay. Now, the paper didn't stop here. They proved nicely this theorem, and then they formulated open problem. Well, the numerical experiments suggest two things in that paper. That first, it's not only that we have inclusion here, that it looks like that if K is continuous throughout the domain, that the image of the domain is the whole spectrum. And the second, that of course, in numerical experiments, we only compute with matrices, so we only compute with eigenvalues. So the question was, what is the relationship between the eigenvalues of matrices, finite dimensional, and a spectrum of this bounded invertible operator, which is a non-compact operator? And this spectrum can be the whole interval, or definitely can include an interval. So includes also a continuous part. So that was the question posed in the paper, and that was the question that I was asked by Kent André. So that was 2018, and in 2019 there was a paper, a joint paper with a very nice collaboration. That was where COVID started, and we never met together. So this all collaboration was long distance, and I think it was very, very intensive, very, very nice. I really liked that very much, and it was also a large part was done by Tomas. It was a part of his PhD thesis. What is the main theorem in that paper? So now we are not talking about infinity dimensional spectrum. We are not talking about the spectrum of infinite operator, but the spectrum of the discrete operator. Okay, about this preconditioned matrix L inverse A. And the theorem says, let's have a conforming finite element discretization. That's all. No other assumption. And AL are the standard representations using this discretization. Lambda 1 to lambda n are the eigenvalues of the eigenvalues of this preconditioned operator. Okay. Now let K be uniformly positive. That's just assumption at the beginning. Bounded and piecewise continuous. This is just a technical assumption. Can be much more general, but it doesn't bring any more strength into the theorem. So that's why we keep that one. And the statement is, then there exists a possibly non-unique permutation such that the eigenvalues of this matrix actually can be paired with the images of the supports of these individual basic functions when we use the function K for taking this image. Okay. So we take the images of the support, and in all this image there must be one eigenvalue. Not saying that must be at least one, but that we can have one-to-one correspondence. There is a pairing. And of course, here this K is not only an image, it's the infimum and supremum, because the function can be discontinuous throughout this tall, okay, throughout this individual support. Okay, so it's like a convex hull of this image. So this is definitely very nice, because it means that if I have just this function K and I have a discretization and I compute this, so I have estimates for the eigenvalues. And even stronger. We don't have time for the proof or even saying how it is based, but there are two ingredients, and the proof is, to me, it's very interesting because it combines perturbation argument, that means analytic argument, and combinatorial argument. Of course, because we have here pairing, so it must be a combinatorial argument. This is just the bipartite, Hall's theorem about bipartite graphs. So we are using perturbation argument to show that sufficient and necessary conditions for the existence of this pairing holds, and that's the end of the theorem. Okay. Well, here are just pictures taken from the paper. There are a couple of other pictures. Simply it's just the illustration. It's clear that if you refine the discretization and the function K would be only mildly changing through the individual supports, you will have very good estimators for the eigenvalues. Okay, here you have all kinds of discontinuous functions, etc., etc. I think it's just no. So what is really interesting is what does it really mean? What about if k is constant over some support, or the couple of supports about some patch? Well, that means that we do have an eigenvalue exactly. We don't have an approximation, not an interval, because then the maximum and minimum or supremum infimum are the same. So we do have eigenvalue exactly. And that means that if we have number of supports over which this k is constant, then we have eigenvalues exactly including multiplicity. That means that we a priori, just be looking at this PDE problem, we know that in our model problem, we must have this eigenvalue equal to 1 with multiplicity about 2000, and we must have the eigenvalue equal to about 160.45 with multiplicity about 2000, and a little bit in between. So we know that a priori without doing any computations. Okay. There is also other approach inspired by this paper, and it appeared a year later by Ladecky, Kulturova, Zeman, that use Rayleigh quotient for doing bounds. Not they don't have this one-to-one correspondence, but the results are very nice as well. Okay, what are the open questions that you make? First, what about tensors and indefinite problems? Because up to now we were definite. So, and what about if you go to more complicated functions? And the other, so can the whole spectrum of the infinite dimensional precondition operator be determined? That means that's the question posed already in this paper by Tveito, Hackbush, and Nielsen. And what about more dimensions like 3D? This has been partially resolved. Some results can be easily extended. Other results we don't know. But they are in the node that has not been unfortunately published yet. Okay. Good. So that leads us to the second paper. So in the second paper, we return back to this infinite dimensional case, and we try to say, okay, try to resolve this question whether we can generalize to non-definite problems and whether we can generalize to say tensors. And we are infinite dimensional. Okay. So the main result, the setting is we just consider this operator where k is now, because we are in two-dimensional domains, so 2 by 2 matrix, symmetric. Okay. So then we can have a spectral decomposition of this, and this diagonal is simply determined by two functions, kappa 1 and kappa 2. This kappa 1 and kappa 2 can be very different. It can be constant, for example, different values of the constant. So you can see that they can kind of mimic some different coefficients of the material or whatever. And the main theorem says, let the symmetric tensor be continuous throughout the closure. Then the spectrum of this operator is given by this interval. So the spectrum of this Laplace preconditioned operator is essentially the convex hull of the images of omega bar through kappa 1 and kappa 2. Okay, that's something what one would expect, or what they suspected in this original paper. But there is something more here. What about if kappa 1 is, say, a constant, much smaller than kappa 2? That it means that in this case, actually, this would be the convex hull of these two constants, the whole interval between them, you know, which in some sense is a very bad message for the Laplace preconditioning. Moreover, if you will dig into proof, which is not trivial, really, so one of the lemmas in the proof says, assuming only the symmetric tensor is continuous at least at a single point in omega, only at one point in omega. And we have this case that the supremum of kappa is less than infimum, kappa 1 is less than infimum kappa 2. That means that the images don't interlace, okay, or that don't overlap, sorry. That there is a gap between these images. So if we have this continuity at least at a single point in omega, then this hole between kappa 1 and kappa 2 must be in the spectrum. So this really looks like a discouraging issue, because this shows that for our model problem, it means that we have these discontinuous coefficients. Say we can see that we have little smoothness between them, so they are continuous but with very different. So then it can happen. Then it happens that the spectrum of the preconditioned operator is simply an interval. So, and this interval can be very large, and it is large comparing to the incomplete Cholesky, because it is the whole interval between 1 and 160.42. Okay. So why then the convergence of the Laplace preconditioning is so fast? We return back to that later on. Of course, there is nothing here with the ordering of kappa 1 and kappa 2, doesn't matter. It's about the question about the whole. And now, so if you do some experiments and discretize, so this whole paper was about infinite dimensional spectrum, but you cannot do it otherwise than to discretize. So we discretized and computed the spectrum of the matrices. So we have found that essentially this whole interval is really filled, and doesn't matter whether the spectrum is continuous, whether the kappas are continuous or discontinuous, or simply it is always the computed spectra composed only of the eigenvalues of the matrices. As we refine the discretization, they fill the whole interval, not with the same speed. The convergence is not uniform, but there is no hole there. So the question is there, can we prove that there is no hole? That it really will have to fill the whole interval eventually, if we say, in theory, refine our absurdum. Okay. So that leads to the question that remains. So how do the spectra of matrices that represent discretized preconditioned operators approximate the spectral interval? So what can we say about this? And how it is related to preconditioning? That means, can we say something about for good or for not good of the preconditioning? If you have, for example, piecewise continuous preconditioning, can we say something? For the Laplace preconditioning, that looks like disastrous, but this is contradictory to our observations. So what's going on here? So one thing that is important to say is, and I will recall that later again, is that we do not call about approximation of the eigenvalues of this infinite dimensional operator. This is a completely different question. We approximate the spectrum as a complement of the resultant set. Okay, and this is what is important here. That leads us to the final paper. And this paper is going to be published at Numerical Algorithms, hopefully any day. It is already after the Galerkin proofs, so we just wait for being released electronically. And so I'll give you the main results of that paper, just without more details, because we don't have time for any more. So this paper first generalizes the results from the first two papers, in the sense that it just takes more general preconditioning, not just the Laplace preconditioning, but say arbitrary operators of that kind. So we have function k here, function g here, and for this function we just assume that k, for this example actually that we have, so k and g are continuous, but we don't need to have for k definiteness. So this generalized to indefinite, and g, of course, we need uniform positiveness because we're invert. And then it's proved that the spectrum of B inverse A is infinite dimensional spectrum, can be defined like that. That's what one would expect, and the proof is just mimicking the proof from the previous paper. It's not a big deal. As for the discretized matrices, the same is true. Okay, so again, we can have a general functions g and k. Now we don't have any continuity, so before we just assume the continuity to have a simple statement. It can be generalized for less simple statement, but with less strong assumptions. But here we just have piecewise continuous functions. That's all. And again, for K, no other assumption. For G, we need uniform positivity. Okay. And then we can prove the same thing for the discretized matrices. That means that if we have discretization with n degrees of freedom, we have an operator, preconditioned operator A preconditioned by B. So this is the matrix, of course, represented. And then there is this pairing between the supports, between these intervals and the individual eigenvalues. That means, again, we can bound a priori the eigenvalues of the discrete matrices, preconditioned matrices, just by looking at this value of these functions K and G over the domain. But the main result here, and many other things can be done, but that they can be found in the paper. So there are just slight generalizations of what we had in the previous papers to the more general preconditioners that are relevant, for example, for piecewise constant preconditioners or piecewise continuous as we have. But I will end up with this final result, the last result, then I will make some comments. But the last result that in the whole generality talks about the convergence of the discrete spectra to the spectra of this whole self-adjoint operators. That can be also continuous. So for this setting, general setting, so we just have infinite dimensional Hilbert space, V dual, and we have two operators A, B, as typically in this PD boundary value problem setting. For A, there is no assumption, no further assumption. We even don't need self-adjointness, nothing. It's just bounded operator, that's it, linear. But B, we need self-adjointness and also coercivity, because of course we need invertibility and we need self-adjointness for defining the inner product. So, and we consider a sequence of subspaces on which we discretize, as we had at the very beginning. So we had the problem and we discretized on sequence subspaces. And this sequence of subspaces has this natural approximation property that we eventually, with refining the discretization to absurdum, we can reach any point in the space W. So this is the standard assumption that yields the Galerkin discretization, convergence of the Galerkin discretization. Okay, so it's nothing extra. Okay, here is the theorem. So if you have the sequences of these two matrices, AN and BN, defined by the standard Galerkin discretization, nothing else, no specification, then all points in the spectrum of this preconditioned operator, B inverse A, are approximated on arbitrary accuracy by the eigenvalues of preconditioned matrices in this sequence. Okay, so that's called in operator theory lower semi-continuity of the spectrum. Okay, so that is for if you have any point in the spectrum and an epsilon, of course, so they exist n star such that starting from this n star, this matrix must have an eigenvalue in this epsilon environment of epsilon neighborhood of lambda. So that explains that if we compute, then essentially any point in this interval is eventually approximated. That's what we have seen in the experiments. So it is explained. Okay. Well, so, but there's still, are things that are kind of bothering, because first I should emphasize again that here we approximate the spectrum of the bounded and continuously invertible operator on this infinite dimensional Hilbert space. Okay, we'll come to that in a moment. But what is the puzzling question? Just return back to our motivating example. In this motivating example, we had for the Laplace preconditioning, we have 1 and 160.45 was the largest eigenvalue. And we have proved that if we smooth this say function a little bit, then we'll get the spectrum, the whole interval between these two numbers of this infinite dimensional operator. Now we have proved that if we discretize, that the discretized matrices, discretized preconditioner actually, will fill in with its eigenvalues this whole interval. So how this convergence can be that fast as we've seen in this experiment? it seems contradictory. It seems that if we refine the discretization, that the convergence of the preconditioner will become worse and worse and worse with the refinement, because the eigenvalues will fill also the space between these two major multiple eigenvalues. Okay, so I just leave it as a question at the moment, because the answer is no. The convergence will not deteriorate, and why we may talk about that in the discussion. Right, just leave it open for the moment. And I come to the final point so that we have some time to discuss. And that is the distinction between the spectral approximation of operators and the PD eigenvalue problem. Because when we started to work on that, we all got puzzled, because we just came in between the spectral theory of operators like we know in functional analysis, but not of the compact operators, of the non-compact operators, because operators are invertible, continuously invertible. And at the same time, eigenvalue problems as they are in numerical PDEs, because in numerical PDEs, nobody is approximating the spectra of the non-compact operators. So how is it? So if you look at this theory in numerical PDEs and approximation eigenvalues, that has physical meaning, vibrations and all this stuff. So essentially, the theoretical basis is the Babushka-Osborne theory that is based on the construction of the so-called compact solution operator. For that, we need two spaces, essentially. We just cannot stay. We must have some space that is larger than the original space in order to formulate the problem and get this compactness. But at the end, what we do approximate are the eigenvalues of this compact solution operator, and the compact operator is only one possible point of accumulation. Okay, so the eigenvalues are distinct. That's it, only eigenvalues. But now we have a problem, because the compact operators are closed with respect to the norm. And as I've said, we have just this, then what we approximate in this numerical PDEs is phenomenon composed of isolated eigenvalues with possibly a single accumulation point. But here we do something else. And we should be aware that if we have bounded and continuously invertible operator, this cannot be compact. Okay. That means that in order to come from the matrices that definitely are compact to non-compact operators, in order to lift any result from this matrix form to this form of infinite dimensional setting, in our case, we must cross this wall of compactness. And this cannot be crossed by the convergence in norm, because the compact operators are closed with respect to the norm. We cannot get through that. That means the only thing that we can have is the convergence, strong convergence, pointwise convergence. And that's also why we have the result that we do have a convergence to any point in the spectrum, but the convergence cannot be uniform. Okay. But we do have a proof that in a special case, like for these functions g and k, we converge not only to any point in the spectrum, but also we cannot converge to any other point. So in this special case that I haven't shown here the result, we have also upper semi-continuity result, which is not possible for other operators, like for example for Schrödinger operators. Okay. So what I like to say is that for this class of problems that I was talking about, we are not interested if we think about convergence of Krylov subspace methods using matrices. The eigenvalues of the infinite dimensional operator are not relevant. What is relevant is the spectrum, the whole spectrum. And this question is drastically different. And this question has not been tackled in this way, at least to my knowledge. So if we wish to really have a feeling what will happen with our preconditioners, operator preconditioners of that kind, then we should look at this whole spectrum. And as I've said, the thing is tricky because there's this distribution function behind, and even if this whole spectrum is the interval, it doesn't mean that the case is completely lost, as we see in the experiment. It is not lost. Despite that you have the whole spectrum, the convergence of Laplace preconditioner for our model problem is very good, and we know why. Okay, I only didn't reveal that. Okay, so that's it. I should, of course, I'm restrictive here only to this class of operators that I have. You don't have anything else for the larger classes. And also, I should admit that I was talking about distribution functions, but we are unable to compute these distribution functions. We only are able to approximate the spectrum, not the weights. So we are able to approximate the so-called cumulative spectral density, which assign to each eigenvalue an equal weight. So that's what we can. But we cannot approximate the real distribution function, which can have a different weight for different, say, operators in this infinite dimensional case. But even this question is important practically, as I've learned from this paper by Lin, Saad, and Yang recently. I didn't know that paper before, but I would like to advertise something else, the work of the others, and both Alex and Matt are in the audience. I think the work that Matt and Alex and Honing did, and which is present in the PhD thesis of Matt, beautiful, beautiful work, allows to compute more, allows to address not only the cumulative spectral density, but also the spectral measure. So which really is fantastic result, which combines beautiful theorem from functional analysis with really very clever approach to computation. So this does something more than we do, but in a different way. So it's not that it covers what we have done, but in some way complements. And I was really thrilled when I learned about this. So I consider that this really very fundamental result, which will bring a fruit for the future. There are many more papers. I just quoted one and the PhD thesis of Matt. Okay, so I like to, when I'm getting old, so I like to end up with this quotes that I think shows, at least for me, how I feel, that really I'm erring and stumbling, on the way all the time, and the only thing what we can do is to hope. Okay, and I'd like to add one more, and it is very relevant to one page on the history that I had, and I had the name of Wallis and Wallis Brownker, and say the starting of the analytic theory of continued fractions for numbers still that time in Europe. And so this in this book that I haven't read, of course, but I have it from that book about continuous fractions in the view of Euler. That's the book by Khrushchev. Says there remain this, we be just skilled in these things that we thought was showing. They will think openly receiving, and whatever it hides, both imparting more properly, I should underline that, by themselves to the wider mathematical community. So I hope that some people will take over and show maybe if there's some seed here, so we'll might develop it later. So thank you very much. I'm very happy that the technology survived, and I have survived too that time. And I'm open to any your question, to any discussion, any objection, any comment. I will be very happy to hear that, and I will be also happy to answer if I would be able to. Thank you very much.
Okay, thank you very much, Zdenek. So is there any questions?
While you're being philosophical, I like a quote from George Forsyth, my thesis advisor at Stanford. Forsyth said, "We'll try and teach you what we want, what we know, and then get out of your way."
Yes. Yes. Beautiful. Yes.
All right. Thanks a lot.
Thank you. Please.
Okay, Peter, do you want to go ahead? We can't hear you.
Can't hear you.
We can't hear you.
we cannot hear.
We still can't hear you, so if you want to go ahead and write it in the chat, we can relay the question.
Okay.
You're very quiet. We can hear you very quietly.
No, the problem.
There we go. That was good. Whatever. We could hear you before. Now you're muted. Okay, so do we have any other questions in the meantime?
Yeah, can I try and ask a question while Peter is trying to do? Oh, okay. But can I go ahead? So great talk, Zdenek. Thank you. I was wondering in the first half of your talk, you're looking at the eigenvalues of the preconditioned, discretized preconditioner times the discretized operator. And then you were showing very nice results. Can you also talk about the discretization of the operator after preconditioning? So instead of discretizing the precondition, discretizing the operator, we discretize the preconditioned operator. Does that make sense? So the Laplacian inverse applied to the original operator, and then you discretize the whole thing. Have you thought about it? And is this something you can think about? And can you say something about the eigenvalues of that matrix?
Actually, I'm not sure how exactly do you mean that, but in the book, if I understand well, in the book with Josef Malek, we did it exactly that way.
Okay.
So we just did everything in infinite dimensional, and the preconditioner was, of course, then defined by the Ritz, by the Ries theorem, by the Ries map, and we discretized the whole thing, not just separately and then combine the matrices. Mm-hmm. But the result was the same. So we get the same at the end, we get the same algebraic problem.
Right, I see. Wouldn't that be nicer though? Because then,
Yes, I know, but it would not be easy to say, because in order to discretize the whole thing, I would need to involve this Ries map, etc., and I would need the machinery. So it's not doable within 1 hour. So.
Okay, great, thank you.
But in this book, you can find it. So everything is infinite dimensional, and then it's okay. What about finite dimensional subspace? What will happen? Okay, then it's discretized.
Can I make comment regarding this discussion? So what you're talking about, it's actually it's integral. It's integral equation, volume integral equation. When you do first continuous preconditioning for continuous Laplace, and then multiply by Laplace in continuing setting, and then do discretization. That is volume integral equation. So that's just a small comment. That's more or less standard thing to do in some communities. For example, like if you want to, like all of us, multiple method is designed for that.
Okay, I don't know whether there was a question or the point.
No, I just comment. So it's not question. I just comment with regard to this discussion. So basically, so just repeat myself. So preconditioning by Laplace, it's exactly in continuous setting. It's exactly a volume integral equation.
Okay, but what about if you have a preconditioned by say piecewise continuous functions? Operator with a piecewise continuous.
Yeah, that's also in that framework, because what you do basically, you just take its convolution with green function of.
Okay,
so
yes, that's true.
Yeah,
that's not a problem.
So that's very well developed in engineering in particular. Very well developed approach. So it's like.
So do you mean that you can have the same results about the eigenvalues of these discretized operators?
Yes. So yeah. Yes. I think.
Can you point out to the literature, please?
Well, I would say I can come. I just cannot have it right. It's not my field. Yeah, I cannot come. I can. For example, you can look up N. Greenbaum's paper. I think N. Greenbaum's paper with. I forgot with whom, maybe with Leslie Greengard. she had something like that, piecewise constant domain, and they did preconditioning with integral equation because they use Leslie's machinery, fast multiple machinery for inverse Laplace. So you can look up at that, and then of course, I can look up also, but just look at volume integral equations, right? And then you'll find it. But look also in Greenbaum and Leslie Greengard paper, maybe 1990s. There is one example. She was basically, as far as I remember, it was pretty similar thing what you're talking about. Not the same as, well, somehow similar, put it this way, somehow similar, right? And there are also big literature they do surface integral equation related to that, because you eliminate when you multiply by Laplace, you can eliminate, say, you have like domain piecewise constant, you can eliminate interior. You can also reduce problem to the boundary. So that would be boundary, but it's pretty much related. So I can look it up. Yeah, you just also like look it up, volume integral equations. And I'm going, by the way, to householder.
No,
I see. I hope to see you there. All right. Okay. So look, if you don't find anything, I may also look, right? But I'm pretty much sure there is what it is. Okay, thanks.
okay.
Okay, so we
Thank
have
you.
Peter's question in the chat. So this is, can anything be said along the same lines if K of X is a random field? Maybe not in general, but for certain probability functions.
We haven't thought about that, but these assumptions that we had in there were kind of artificial. So we really don't need this piecewise continuity. Okay, it can be done for general measurable functions. So possibly yes, I don't know. We just haven't thought about that. But this was just for having the results a little bit kind of more clear to formulate it for kind of simple thing that were posted in the original paper to the model problem. So that's why we had these assumptions, but there is nothing. So if you look at the paper, so we just have a Riemann measurable, functions. We don't, Lebesgue measurable functions. We don't need anything else. So might be possible, yeah.
Okay, maybe I fixed the mic issue. Can you hear me now?
Yes.
Okay, yeah, thanks. If this piecewise continuity is artificial, then I think this carries over pretty much, yeah, I would say. Maybe not with deterministic results, but with in expectation, but then I think it will carry over, yeah.
Maybe I can say a bit about this piecewise continuity, because there is no word about granularity of this. Okay, so we can refine that up absurdum, this piecewise continuity, and also this example. So why this, which I left open? Why this? Say we converge that fast, and with the refinement of the mesh would not change that. Well, because we'll always keep this proportion of these eigenvalues that are at the ends of the interval and inside. With the refinement, because these eigenvalues that are inside of the interval are only related to those supports that cross these discontinuity lines, not the others. So that's just that they have measure 0 with respect to the others. So it's just a fast comment on that. So yeah, we haven't thought about that, but I think it should be doable. Yeah.
Okay. Thank you.
Okay, we have time for maybe one more short question, if there are any. Okay, go ahead.
Just a silly question. Thanks first, Zdenek, for your very nice talk. I found this extremely exciting. Silly question. how do you construct the preconditioning, Laplace preconditioning? How did you make your numerical experience?
Over there? Oh, no, it was
The discretized Laplace, how you precondition with that?
Yes, that's what we do. So the infinite dimensional operator is just the weak formulation that's in the standard discretization. That's what we did.
Okay, so you go really for the spectral decomposition or something like that, or?
You mean for the computation, or?
Yeah, for the computation, yeah.
No, for the computation, you just get a matrix, and we just apply the preconditioner as a solve the preconditioner in the standard way as you do with any other preconditioner. So you have the matrix A, you have the matrix B. Okay.
Yeah, sure, but you need to invert it, no?
Yes, yes. But this is in this simple problems. This is easy. I mean, this is not a problem. So you mean that about the numerical problems, or here?
No, I was just curious how you do that.
No. It was just a toy problem for the computation. So we didn't really care much about the refinement of how it should be done. Of course, in practice, you will not do it in this way how we did. So we didn't do the spectral decomposition or something. Honestly speaking, I don't even remember how we did it, but how it is in the software done then. But that was that would not change any picture if you do it this way or that way. So for this toy problem, not for the practical, of course, it must be done differently.
Okay, thank you.
Okay, so we are just past 5 o'clock. So thank you very much, Zdenek, for a very exciting talk, and thank you everyone for a very stimulating discussion. And we hope you'll join us next week. Next week we'll have our last ENLA seminar before the break. So the speaker will be Daniel Krasny. So thank you again, Zdenek, and hopefully see everyone next week.
Thank you very much.
Right, goodbye.